All right, let's define another random variable, another distribution. So let's let chi-square sub nu 1 and chi-square sub nu 2 be independent chi-square random variables. So each one of these has a chi-square distribution. Again, so you could think of this this guy as being like it's sort of like you take some independent normals, independent standard normals, and you take nu 2 of them, okay? You square them and sum them up, okay? Similarly for this one, except nu 1 terms. You're interested in the behavior of this sum of squared standard normals, okay? So if these guys are independent, having these degrees of freedom, well, if you take one of them and divide by its degrees of freedom, and then take the other one and divide by its degrees of freedom, this thing has what's called an F distribution with nu 1 numerator degrees of freedom and nu 2 denominator degrees of freedom. That's because nu 1 appears in, well, hey, you know what? Actually, nu 1 is sort of in the denominator, isn't it? But it's in the denominator of the numerator. Anyway, it's up. We write it up here like this, and then we put this one down here. Anyway, whether you like that or not, that's how it's done. Nu 1 numerator degrees of freedom. That is a nu, by the way, and nu 2 denominator degrees of freedom. So the utility of this is well, there's several things that make this guy useful, but so, if I write down, f is like this chi-square random variable with, it's equal in distribution to this, right? Chi-square to divide by their degrees of freedom. Okay. Now, all of this, I know that by that theorem that we stated earlier, that's proven in your book and various books, that there's this nice quantity n1. If I take a sample of size n1, subtract 1, then multiply by my sample standard deviation, which is a random variable, and divide that by the population variance, this stuff behaves. This stuff behaves like one of these random variables, right? Okay, so now I'm going to divide by the degrees of freedom there, which again, that's n1 minus 1. And then similarly, in the bottom, I have n2 minus 1 times the sample standard deviation for the second sample. Divide that by sigma 2 squared, the population variance for the second sample, or the second population, sorry, and divide by the degrees of freedom there. And again, so this, this stuff behaves like this. Because this behaves like this and this behaves like that, and so then that's why we write this equals with the d there. It's equal in distribution or equal in behavior. Maybe if if you have a problem with your B's and D's, maybe you could think of this as it's like that. Equal in behavior, equal in distribution. No, just kidding. We don't do that. We do equal in distribution. Okay, so let's see. Can we get some canceling going on here? Why, yes, I think we can. This cancels with this. This cancels with that. And we're just left with the sample variance for the first sample over the population variance for the first population divided by the sample variance for the second sample over the population variance for the second population. Okay, this is nice because sometimes you want to look at two populations. Okay, maybe one brand of light bulbs versus a second brand of light bulbs. Okay, and maybe you're interested in knowing something about the ratio of the variances, for these lifetimes of light bulbs, okay, how long they last or something. Maybe for a particular application you want light bulbs that maybe you don't care so much about the mean, but you want their lifetimes to be more predictable, meaning smaller variance. So you want to compare the two variances. Okay, so maybe you could take a sample of size N1 from the first population and a sample of size N2 from the second population. Okay, and then I know that in theory, if I'm sampling from a normal distribution, or if these lifetimes are distributed normal, then all this stuff should have should behave like an F random variable.